Hello everyone, my name is Minas Karagiannis and today I am presenting our work from the National Technical University of Athens titled Characterization and Anisotropy of 3D printed mycelium. Mycelium is by definition the vegetative part of fungus consisting of a network of fine white filaments called hyphae, which serves as the biological binder in mycelium-based composites. As a material, it falls under the category of biomaterials. It is considered to be a living material since mycelium needs to grow to reach its final form. The production of mycelium-based composites aligns with the fully circular economy model. It upcycles agricultural waste, it is manufactured with low embodied energy, and it is fully biodegradable. Its key civil engineering properties include fire resistance, acoustic and thermal insulation, and a high strength-to-weight ratio. The dominant production method of mycelium-based composites is molding. Molds are filled with a mycelium-infused paste, letting it grow until it reaches its final form. 3D printing is a more recent take on mycelium-based composites production. It uses a similar paste, but with slight modifications to make it extrudable. The paste is used as the printing material, and the mycelium reaches its final form after the print. Finally, an emerging but still preliminary alternative is binder jetting, where a mycelium-infused ink is deposited on selected areas of a powder bed. On our study, we will produce mycelium-based composites using 3D printing. The typical procedure of mycelium 3D printing consists of two phases, a preparatory phase and a post-3D printing phase, with 3 steps each. Each step has parameters that can be altered, affecting the final product. The first step is the mycelium inoculation. Different fungal species and different substrates can affect the properties of the 3D printed object. When it comes to the substrate, apart from its composition, its quantity also plays a major role, driving the mycelium to grow with either the so-called guerrilla or phalanx strategies, which in turn dictates the final material's density and print quality. The second step is the primary colonization of the mycelium. Here, the key parameters are the conditions under which the colonization takes place. Mycelium growth is favored in room temperatures in dark and humid environments. Depending on the previous parameters, we are able to move to the next step from anywhere between 3 to 15 days. Mixing, the third step of the process, converts the colonized substrate into a printable paste using gelling agents to ensure sufficient viscosity and yield stress for stable extrusion and high print fidelity. Among the most common binders are psyllium husk powder, chitosan, agar, and different kinds of gum. The fourth step is the 3D printing itself. Clay printers are used, although on many studies a custom formation was created. The print parameters are critical. Variables like nozzle diameter, print speed, and layer height directly influence dimensional accuracy and mechanical anisotropy. However, the range of these parameters is fairly wide. After the printing has been completed, the printed object is left aside for a second colonization phase, which is the fifth step of the procedure. Similarly to the primary colonization, the parameters that can alter the final results are the environmental conditions. Again, we see a clear preference of room temperatures and dark and humid environments. The last step of the procedure is the ceasing phase. Here, the growth of mycelium is terminated. There are two ways this can be done, either by drying or heating the mycelium. Heating permanently kills the fungus, yielding a stable, inert composite. Drying hibernates the fungus, retaining its capability for self-healing or damage repair upon re-exposure to moisture. However, mycelium 3D printing comes with its challenges. First and foremost, there is a high risk of contamination, making the product hazardous both mechanically and health-wise. The risk of contaminations is present in almost every part of the procedure. Studies mention that in order to avoid contamination, heavy lab equipment is needed, such as autoclaves and laminar flow cabinets, while strict sterilization protocols must be followed. Thankfully, other studies claim that it is possible to 3D print mycelium even by following a minimal sterilization process, namely wiping the working surfaces, tools, and printing parts with isopropyl alcohol. Another major challenge is the inability to directly print complex geometries due to the low grain strength of the wet paste, leading to gravitational collapse. This is overcome by separating and biowelding. The geometry is divided in several easily printable parts. Each part is printed separately and it is left to be colonized. Then a coat of the very same printing paste is applied to merge the parts, forming a single monolithic structure. Last but not least, perhaps the most difficult challenge to overcome is upscaling the process. Molded mycelium products have been mass-produced, but such thing hasn't happened yet for 3D printed mycelium. This is mainly because of the previously mentioned challenges, as well as the fact that 3D printing with mycelium is still a fairly recent practice. Moving on, we present two very influential studies. First, we have the study of Luo, Yang, and Peak. They have created a custom, low-cost, open-source hardware alternative for 3D printing with mycelium, which they called FungiBot. Using FungiBot, they printed many examples, highlighting both the advantages of mycelium 3D printing, such as its biodegradability and replace of plastic products, for example, packaging, as well as the ways that we can overcome the posed challenges. Also, the authors have calculated some mechanical properties of the printed product, both before and after the colonization, as well as the stress-strain curves for tension and compression, and compared the results. We can see that after the colonization, the tensile strength and Young modulus decrease, while compressive strength and compressive modulus increase. The second important study is that of Modonlu and others with the title Tilted Arc. This study focuses more on structural design strategy rather than creating a stronger mycelium-based composite. This is a proof of concept study for a load-bearing structure. Mycelium-based composites are weak in tension, as we saw earlier. However, the arc design bears load only through compression, working around the material's weakness. 4 different treatments of mycelium-based composites were fabricated, choosing between sawdust and shredded paper as the substrate, and between guar gum and Arabic gum as the gelling agent. For each treatment, the yield stress, Young modulus, and behavior of the material were recorded, offering useful insights on mycelium-based composites. Unfortunately, we do not yet have any results of our own to show, so instead, we will explain the experiments and the goals of the study. On our study, we will create a bunch of specimens varying the parameters mentioned earlier, both from the preparatory and the printing phase. We will do a thorough mechanical characterization, and we will utilize the Taguchi method to calculate the importance of each parameter with the fewest specimens possible. Then, for some optimal combinations, we will further characterize the material. The studies on mycelium-based composites are largely application-oriented. Our study contribution is a more fundamental one. To our knowledge, there has never been such a systematic study on characterizing 3D printed mycelium. We aim to gain a deeper understanding of the behavior of this highly promising material, figuring out how each parameter affects the final result. On future studies, fatigue and creep tests can be conducted, while an ultimate goal would be to construct a prediction model, minimizing the trial and error phase for finding the suitable solution on the multivariable problem of setting the right parameters for obtaining a desired result for its application, and at the same time giving the ability to simulate the material on finite element analysis. I want to thank you for your attention. Now, I would be glad to answer any questions you may have.